Okay, so, all right, so it should be recording now. Perfect. Okay, so this is the start of the energy storage module. There is a lot of information to cover. So what I've tried to do is just select a few topics that are relevant to modern day batteries, because I imagine that's what you're most interested in, but also it's a huge materials problem. And the problem is full of challenges that material scientists can play a leading role and really core to the climate change problem, the energy storage problem, and development of new materials as solutions for resolving the issues that all the issues that we have. So instead of doing sort of like a flyby, here's all the topics of energy storage, I'm going to focus more on modern day, like lithium ion batteries, but that's not to say, and you'll see through our discussions, that's not to say that that's the only flavor of battery that is the most important. Is just dominating portable applications and electric vehicles, right? So I'm just going to go deep dive into that, focus on the materials aspects, but certainly some of you are mechanical engineers on this in this class, so there's a huge number of things that we can tackle in regards to developing, the next generation battery. To address some of the questions and continue on what we discussed, in the first intro lecture, there are a few questions about, which battery is appropriate for which application. I won't be able to get to like all of that and in the few sessions that we have on energy storage, but I will try to focus and do a really deep dive onto electric vehicles and portable applications. That's not to say grid storage isn't extremely important, and given the natural disasters that we've seen occur recently, grid storage is actually really an emerging area that we need to tackle as well. So that's a lot. I wanted to note, so I have a lot of references. We don't have a textbook for this class, as you already know. So a lot of the information that I'll be talking about are from recent review papers, journal articles, like very much state-of-the-art developing information. So research. And so what I've tried to do is aggregate all of those papers and resources, whatever I cite in PDF, and uploaded it to the OneDrive directory. I didn't upload it all to Carmen because we do have a limit on the size of our Carmen page, but also it's just easier to like download everything at once on OneDrive, so you can just grab it all. This directory will actually be updated as we go. The majority of the papers are already in there, but if there's anything new that comes up, I will add, because every day the energy landscape is changing. It's quite dynamic. So you'll see some of the papers that I cite, came out like a few weeks ago. I wouldn't have been able to like give that kind of, talk about that kind of research and technology development a few weeks ago. So it's a really dynamic field, but some of the papers you'll see are from like 1958. So, it's also very old. This is sort of a segue into also getting references for yourself. You all are at least fourth year and above, and so you're pretty familiar at this point, regarding primary sources and things like that. But if you weren't already familiar, beyond Googling, which is a very fine and great way of finding papers and popular science articles and what's out there, what's developing, I just want to draw your attention to some resources that I find very helpful. All of them are actually free, but I put free in quotation marks because the university already pays for the license, so it's free to you, but all of our fees in some way go to these services, like grant money or what have you, and student fees, things like that. It all goes to getting you these resources. If you haven't already been using Web of Science, I highly encourage you to do so, because there's a lot of ways that you can look at for papers and review articles. If you want to know what's the most highly cited work in the area of lithium ion battery, what's like the single most seminal paper in this field that's a review paper or just somebody's work, you can find that out through Web of Science. It's a really good database. Google Scholar, some of you may or may not already use this. When you use the Google search engine, Scholar will come up. And honestly, sometimes just Googling, just seeing what's out there, that's also very useful. And I'm spending a little bit of time on this because eventually we will actually be discussing your term paper and your group presentation as well. And when by term paper, I mean your own development to the technological idea that you think is going to, dominate the energy landscape, whether it be renewable energy harvesting, conversion, or storage. Interlibrary loan. If there's ever anything that you can't find or it's somewhere else, this system through OSU will deliver the PDF, to your inbox. They'll go get it from some other university that does have it. It's a web of system that will, so if for whatever reason OSU doesn't subscribe to a journal article that you really want the journal, then they'll get the journal article for you. You just have to request it. And then I don't know, honestly, how many of you actually still do this, but I still do this sometimes, actually just physically going to the library and opening an article, opening a journal. You never know what you'll find there. And then some popular science too. I mean, we'll talk about, the technical aspects and sort of just get through the hype that is that's built up in popular science articles, but sometimes it's useful just to see the technology through the lens of a layperson and see, where are the needs, what's the interest. So those are my top 6. If anybody has additional suggestions, feel free to include that in the chat or in the group discussion on the Carmen page. Okay. So not a lot of information, technical information there, just helpful resources. Also, here are some screenshots from Web of Science on how you get to it. So library.osu.edu is going to be your friend in this regard. There are plenty of databases. So if you click on the databases, you'll see that Web of Science is under W, but there are other databases that I don't use as often, like SciFinder, things like that. That you may have used for your other classes or research or what have you. But yeah, you click on that and then you get to, you get to this page. And here I had an example of grid storage. So in the screenshot that is barely legible, you'll see that you can cite, list it by, highly cited papers, review papers, hot papers, other, papers that are being cited a lot. What are other people reading? Very helpful site. So you can see that this, well, you can't see because it's quite small, but it says, electrical energy storage for the grid, a battery of choices. It's been cited 8,000 times. So this is a paper that people read often. You might want to read it for yourself as well if this is something you're interested in. Okay. So with that, I'll jump right in. Any questions about that or any comments? Anybody want to jump in about that before I move on? Alrighty, so silence. So I will move on. Feel free to put your questions in the chat if that comes up later. All right, so batteries. There's a lot to be said. There's a lot of work that's been done, since the days of, well, perhaps not intentionally, but the Baghdad battery. So who's heard of the Baghdad battery? I see a shaking of the head. Oh, okay. I see one hand raised. Okay, so there's 2 responses out of 20. So, all right. So, 50% of the 2 people have said that they've heard of it. Well, it was discovered in the 1980s or so, 1970s maybe. It was an archaeological dig, and they discovered that in this terracotta pot, someone, for whatever reason, although the purpose was unclear, could have been electroplating of some sort, but there was a copper cylinder and an iron rod in potentially some acidic medium of sorts. And so this was this archaeological find was basically indicative that this could have been the first battery. I mean, it wasn't used as a battery, that I don't think, based on the historical evidence, but it's an electrochemical cell of some sort, right? And so here we're going to start drawing the distinction between what is a battery and what is an electrochemical cell, because you can drive current, you can apply current and measure voltage, so you can drive this electrochemical process in some sort of direction, in some sort of way. And so that's sort of like the first inkling that, okay, people, civilization, society was trying to do something electrochemically, right? Combining electricity and chemicals, or converting chemical energy into electrical energy. And then our favorite scientist, Benjamin Franklin, who's the one who first termed battery. So when I talk about these reactions, like lithium-ion battery, really I'm talking about the electrochemical cell itself, right? What is the chemical reaction that is happening? And how is it converting chemical energy into electrical energy? That's really what I'm talking about. You probably have also heard the term battery in other contexts, like a battery of experts, right? A group of experts, or a battery of something, it's a group of something. So an electrochemical cell, when you can connect them in parallel or in series, right, can be a battery. And so if we're just talking about like one cell, that's what I'm talking about. I'm talking about, okay, we're just going to talk about one cathode, one anode, one electrolyte, and we're going to talk about one electrochemical cell. And then when you combine them all, that's really a battery. Although in sort of layman's term, you probably hear it a little bit interchangeably. A battery and an electrochemical cell is basically the same things these days. So that's the context and the distinction between electrochemical cell and a battery. All right, so we're going to fast forward through a lot, but I just wanted to give you all context as to where things, how far things have come and how far things have accelerated. Technological development has accelerated, right? So Alexander Volta, which we know is what volt is, the unit of volt is named after, right? He's credited to be the first one to develop an electrochemical cell, with the frog twitching. Then 1860s invention of the lead acid battery. So this was a common battery in vehicles. Sorry, not electric vehicles. In automobiles. Of course, there's a lot of discharge, a lot of current leakage that ultimately makes it not in low energy density, that makes it really not viable for electric vehicles. I'm also going to peruse past a lot of these things to get basically towards lithium-ion batteries. That's not to say that there's a huge industry for nickel cadmium still, nickel metal hydride. What the metal in nickel metal hydride is a number of things, intermetallics, alloys made up of like nickel, chromium, yada yada. So there's a lot of chemistry there. So I just fast forwarded from like 1860s all the way to basically 1990. So that's a huge source of time. And then we get to lithium-ion batteries, right? Commercial lithium-ion batteries from Sony in the 1990s, specifically 92. But the work that went into, the path to commercialization actually started in 1980 with the seminal work of John Goodenough and understanding ion conduction in lithium cobalt oxide. So that work was funded by the Air Force Office of Scientific Research. And so it was really fundamental. It was just, how does an ion move through a crystal lattice? That work in the 1980s, in 1980, basically led the way to commercialization by Sony. And then since then, who has heard of lithium iron phosphate or iron phosphate or LPO as it's sometimes called, or even A123? Okay, so there's a yes, there's a no. Okay, great. We're still at 50%. Okay, so half of the two people that answered have heard of A123. So this is obviously a newer company. 2001 20 years ago. So depending on what timeline you're looking at, that can be new, that can be old. Obviously, in this timeline, it is very new. And it was heavily, A123 was heavily backed by the Department of Energy to develop, alternative technology to lithium cobalt oxide. And we'll go into the all the geopolitical and also just material challenges of cobalt. Some of these issues you may or may not have heard of because it's been popular in newspapers and in the press about how complex it is of a manufacturing process to get cobalt and to get lithium, actually. And basically, we as a materials community need to develop materials alternative to cobalt and potentially to lithium as well, right? But these are the dominating materials that lead the way for lithium-ion battery, and that's what's in the electric vehicles that you can buy these days from a variety of companies, not just Tesla. Okay, and then more recently, just 10 years ago, right, silicon nanowire development. So that's focused on the anode. So I've thrown a lot of terms out there like cathode, anode, electrolyte. Here are some metals, right? So we're gonna start off with trying to understand, one, the exact definitions of these things, so that when we talk about all the challenges, that we're very technical and specific about these material systems. Okay, so that was like 300 years worth of history of battery development. Any questions so far? Okay, great. We're going to be focused a lot on lithium in this class, and so I just have here a brief history of lithium, and as an element. For a while it wasn't that interesting. It was discovered a long time ago, 1817 to be exact. So it's been it's been known for a while, and people have gotten it from basically extracting lithium metal itself from ores. But that is actually really expensive in terms of cost, in terms of energy, how much it takes to get the lithium out. But we've been dependent on lithium because it has high specific capacity. So we'll talk about that. I bolded that word because we need to talk about what that means. So that's that's the capacity if you use a lithium anode, right? As opposed to what is commercially available now, which is graphite and a little bit of silicon as well. So one of the reasons why lithium ion has really just taken off despite all the other technologies, and despite its costs and despite the issues of mining cobalt, is because it has one of the highest, you can get one of the highest specific energy. So that's normalized by the mass, so gravimetric specific energy, well, okay, that's redundant. Specifically, you can also get really high specific power. So that how many watts per kilogram, right? So there are other technologies that involve elements that are more abundant in the Earth's crust, that are cheaper. Here you see sodium sulfur. Sodium is highly abundant, right? I mean, sodium chloride, you can basically just go out, to the ocean, get some seawater, evaporate off the salt, evaporate off the water, get the salt, and then just get the sodium that way. That's actually not that expensive of a process. That's not energetically expensive. And sulfur is also actually really cheap because it's a byproduct of petroleum refinery. So there are cheaper options, but they don't always offer as high specific energy or specific power. So what we want to be is we want to be in this region here where we're just trying to maximize things. And these metrics, when you increase the x-axis and you increase the y-axis, you're able to get out a lot of power very quickly, so higher specific power, or you can use your device for longer, or you can drive for longer distances before recharging. right? And it's light. Lithium is extremely light relative to some of the other technologies that are listed here. So on the other end, I want to point you to this vanadium redox flow. So that's part of grid storage technologies that we'll talk about in the grid storage part of the energy storage module. There is still a lot of value in studying technologies that don't always increase the x-axis or increase the y-axis for you. There's a lot of interesting chemistry there. And now people are moving away from vanadium because it is expensive and because it is not as earth abundant, and using iron, right? So just because something is not off the bat, you know, the least expensive, there's still, or, you know, will yield as high, you know, specific energy or specific power, there is still value to do some fundamental research to understand the chemistry that can be translated to a system that is cost effective. Because at the end of the day, right, if you're working on energy storage solutions, right, they're solutions. That means they have to work for some application. There is no holy grail, by the way. If you read popular, you know, media articles about, you know, some people are searching for this holy grail. There's no such thing in energy storage. If you have an application, you develop or you go find the energy storage solution for it. There's no one size fits all, right? So those that are working on lithium ion battery technology, you know, that's fine for let's say electric vehicles. But if you're trying to power, you know, a city, it's that energy storage solution might not be will not be the best solution. So there's no holy grail, there's no one solution to everything. Okay, so really it's going to take a combination of all of these energy storage solutions coupled with renewable energy conversion and harvesting to really, you know, make a dent in climate change. Okay, so here's the overall learning objectives for all of energy storage. So not just for today and not just for lithium ion batteries. So what we're going to cover is all the following topics, right? So hopefully by the end of this module that you'll be able to identify historical milestones. So that's something that we just discussed in energy storage. We'll also talk about how to calculate energy storage, talk about the scale that's needed for a variety of technological applications. Like if you wanted to drive to Cleveland and back and didn't want to charge your electric vehicle, how many cells are you going to need, right? And then also identify definitions of battery terminology, identify state-of-the-art cathode, anode, electrolyte materials, identify battery material synthesis methods, right? So what are the ways that we make these materials? And then also identify pertinent materials characterization for diagnostics of batteries, right? How do we know a battery failed, or how do we know if we can recycle a battery, and what's the state of health and state of charge in a battery? And then also identify the modes of failures in batteries. There are so many ways a battery can die and fail, and not always in a spectacular way like all the Samsung phones, right? So, and honestly, those aren't the failures of the batteries. That was actually a failure in architectural design of the casing that went around the battery. Of course, when the casing failed because of bending of the aluminum case, that's when the battery inside the phone short-circuited, and then the liquid electrolyte combusted due to thermal runaway, right? So there were actually a number of issues that led up to the failure of the battery, but the battery itself was not the issue in the Samsung phones, you know, going up in flames, right? So here's a representative figure summarizing everything that we need to think about when we think about modern day lithium ion batteries. So in terms of materials, right, you have the positive electrode or the cathode, you have the negative electrode or the anode, You have the electrolyte, so that will help transport the ions, from one electrode to the other, and all the considerations that go into selecting these type materials. So here's lithium cobalt oxide. We will talk about that a lot as a representative layered material for ion conduction. We'll talk a lot about, excuse me, about graphite as the leading anode material. And then we'll also talk about the liquid electrolytes that have been used historically, although that landscape is also changing because technology is moving towards solid state batteries as well, and away from a very mature area of battery development, which is the liquid electrolyte development. Okay, so speaking of lithium cobalt oxide and John Goodenough, how many of you are aware that of the Nobel laureates from 2019 in chemistry? Okay, so we see two. I see two. A third one is no. Okay, I think that's a third. Okay, so about 75% of those who answered said they were aware. This was in the press. Okay, so two. So, okay, 3 out of 5. So the percentage is decreasing. This person is still alive, by the way. He's 95 years old, I think, at this point. He has been working on lithium cobalt oxide and also battery in general for a while. But he wasn't always in the battery field. I have to say, he actually started studying just metal oxides and just fundamental physics of materials. And then 1980, he developed the cathode cobalt oxide and looked at it at a molecular level, as in studying where lithium ions can be housed in the crystal structure of cobalt oxide. Right, so that was his contribution, and that's what he won 1/3 of the award for. And so that obviously has had significant impact in our society. So that's a huge contribution. So Stanley Whittingham, also still alive, he worked on materials where he looked at also cathode materials, but titanium disulfide, so TiS2, also a layered material that can house lithium ions in its crystal structure. He also looked at the fundamental mechanism of ion conduction. So that was his contribution. Of course, we don't use titanium. The material science community, have not commercialized titanium disulfide because lithium cobalt oxide has actually a higher voltage and thus higher power for commercialization. And then Akira Yoshino won the other 1/3 of the prize, and he developed the carbon anode. So that completes, well, we haven't talked about the electrolyte, but that completes the 2 electrode, the set of 2 electrode materials, and how the carbon material can house lithium ions when you shuttle lithium ions back and forth. So those were the 3 prizes for in chemistry back in 2019. So pretty recent, even though all these technologies and research have been done for quite a long time. Okay, so 3 very important people in this area that we're talking about. Okay, so when we talk about figures of merit, when we talk about what is a good battery, there is no such thing as a good battery, right? There's no such thing as a bad battery either. If your car doesn't turn on, it doesn't turn on, right? Then it's a bad battery. But when it works, it's a good battery. So instead of talking about the qualitative descriptors of a battery, right? We talk about how much energy does a battery have. So watt hours per kilogram. So what's the energy in a system as normalized by its weight, right? So you can So if you're trying to lightweight your battery, then you want, to use, well, lighter materials, or you try to get more energy out of the system if you're using a heavier element. We also want to talk about a battery's voltage, right? That will be an indication of how much power you can get out of a battery. And also shelf life, right? How many years do you have to use this battery? So here's some metrics that I grabbed from the two publications that you see down below. So there's alkaline batteries. So that's more of like the AA type batteries that you've heard about. And then there's some other chemistries that you probably haven't heard about because they just weren't as commercialized, like lithium iron sulfide, lithium manganese oxide, and then the sulfates. So those are examples of primary batteries. So what that means is you use it once. Can you recharge a battery? Can you move the ions back and then discharge them during service again when you actually need to power your electronics or power your vehicle or whatever? Those types of chemistries, the answer is no. You could try, but most often, these batteries are for one-time use. So they're primary batteries. The secondary batteries are what we're interested in, the ones that can be rechargeable, right? So lead acid battery, dominant in vehicles for a while. So if you want to be able to unlock your car or things like that, or like the residual, rolling up your window, that kind of thing, or rolling down your window, right? That uses lead acid battery. So here the energy density, the gravimetric energy, so that's normalized by mass, is 30 compared to nickel metal hydride, so that's 60. So already we've increased 2x in energy. And then you jump all the way to lithium cobalt oxide, because lithium is so much lighter, you jump up to about 200. I mean, this is a sort of a floating number, right? I mean, the technology is developing by the day. So this number is increasing by the day, in terms of, what we can engineer this material to do. Then there's lithium sulfur. So you can just say, well, we have so many issues with cobalt, then why don't we just replace it with sulfur? An element that is much lighter, that's really inexpensive. And in fact, the petroleum refineries in Canada, in Vancouver, will just give this, basically sell this material to you for, like a cent a gram, or even less than that. I mean, it's ridiculously cheap compared to cobalt. And you can get out you can get out 2,500 watt hours per kilogram there. So you can see the jump in energy. So the question becomes, well, it seems obvious that we use a very light element for the cathode, like lithium, anode. And then we use a very light element like sulfur relative to cobalt, right? And we get an increase in energy. So one of the reasons why lithium sulfur hasn't been as widely commercialized is because there are different challenges to designing that kind of battery. You have to have a different electrolyte. You basically change your entire manufacturing scheme as opposed to lithium cobalt oxide, right? The other challenge is, well, you pay a price in power a little. Your voltage decreased from 3.5 volts to 2.2 volts for lithium sulfur. And then in terms of cycle life, how many times can you cycle this battery? Well, not so great for lead acid, better for nickel metal hydride, better for lithium cobalt oxide. There's a question mark for lithium sulfur because there are a lot of data in terms of laboratory research. But in terms of, a commercializable cell that you can cycle back and forth, that number is more of an unknown. There's a larger range of numbers that have been reported. And in terms of, verifying these numbers, that's, yet to come in a commercial cell, right? But there's a lot of research that's already been done on this, and people report, left and right, like 1,000 cycles or 2,000 cycles or 500 cycles. But it's still really promising technology. It's more nascent than lithium cobalt oxide. Okay, so here we are again, lithium, but here we've now put onto the same plot that you've seen, increasing in energy density, increasing, so by mass on the x-axis, by volume, right? So volume might matter to you as an engineer if your application is something that's portable, right? Nobody wants to carry around a massive battery just to get more power or just to have more energy in a system. But if it's for grid storage, maybe it doesn't matter. You know, if you're in the middle of the desert somewhere and you have a lot of space, that's less of an issue volumetrically, right? But a lot of times we do want lighter and smaller in size. The red circle that you see here is something new. So lithium metal, at the time of this publication, right, 2001, this review paper said that lithium metal is unsafe. And so in the last 20 years, there's been a tremendous amount of work to make lithium metal safe, because graphite, you can store less lithium ions, fewer lithium ions in graphite than you can if you just had lithium metal, right? Every atom in your anode is usable because every atom is lithium, right? But so obviously just using lithium itself as an anode will get you lighter, higher energy density gravimetrically as well as volumetrically. But using lithium metal itself, you run into issues like lithium dendrite formation. There's a number of challenges in just using the lithium metal itself. And there's a lot of people working on this issue. And when we get to the anode section of energy storage, which will be in about 2 lectures, we'll talk about all the dendrite formation issues and how to actually stop it, or I should say mitigate it, because dendrite formation is actually energetically favorable. So you're fighting against thermodynamics there. Okay, so we've discussed a lot of that, a lot of the energy storage technologies. One of the questions that someone asked in the first intro lecture was, like, what do we use and for what applications, or like, what I thought about, I guess, lithium coal oxide or Tesla or something like that. And this goes back to my comment about there's no holy grail, right? If you need or want to target a technology that is where you need the energy fast, or if you need a lot of it, to power a city in case of like, a power outage or something like that, what you really want to look at is all the different technologies that are out there. So here you see, okay, for like flywheels, right? So you can deploy 931 megawatt. That's the worldwide deployment in 2018, according to this 2019 reports. And here, electrochemical capacitors, there's much less power that was deployed, but you can get extremely fast. So these types of technologies are good for one needs to not only think about, okay, how much energy do I need, but how quickly do I need it? So if there's a power outage and I have very sensitive equipment, or I have appliances that I don't want to be turned off, then I need technology that will, or energy storage that will kick in like that, within seconds, and then deliver that little bit of energy that I need to keep going in a few seconds. So flywheels are actually good for that, for power outages. Electrochemical capacitors, also really fast, but they deliver, less energy. But that if you have, let's say, a pacemaker or something, and it needs to kick in that very little bit of time in between, glitches or whatever, that's all you need. If you need a backup battery to a battery itself, electrochemical capacitor could be good for that as well, right? And then I think someone asked, what about batteries for like your house, or batteries for a city? So there you really want to look at, honestly, not lithium cobalt oxide or anything like that. You really want to be looking at like pump storage hydropower, where you basically pump, water gets pumped, and that is the stored energy. It's like mechanical energy that's stored. So there, it's the scale of energy storage, dictates what kind of storage technologies that we use. Okay. this is not a policy class, this is not a policy class or anything like that, but I do want to touch upon certain factors that dictate what kind of technologies get pushed to the forefront, right? And so companies, they reside in different states, they reside in different countries. And so the policies of each state and the policy of each country really drives the technologies that are really worked on. So here are just some examples that I found, that are incentives. Europe has a 2030 plan or 2050 plan where there's a proposed bill in the European Union where all cars by 2030 or 2050, I think, that are sold will only be electric. So if you have a policy like that, for sure the automotive companies are going to be pushing, if that bill gets passed, right, that they're going to be pushing for electrification of vehicles, imminently. And some of you may have already seen the headlines that Ford has invested $11 billion in 3 states to develop, to open manufacturing plants for making electric vehicles, right? So there's a huge push in manufacturing of electric vehicles, and they're motivated by certain tax incentives or certain policies that each state has, which also will drive certain companies to open plants in certain states, right? So in terms of energy storage, there's a lot that goes around that surround not only technological development, but also, the policy incentives that are there to support energy storage technologies. Okay, so let's get back. That was a very brief digression into policy and such. So energy power, let's start back there. So in terms of being exact and technical with our definition, right, I've been using specific energy and energy density. The way to distinguish between energy and power, which are 2 metrics to analyze the battery on, is if you think of the analog of water, right, how much water you have in your bottle being the electrochemical cell, how much water or how much energy there is your specific energy, right? That's the confined volume that you have. That's your when we talk about volumetric, we're normalizing by most of the time by the active material, right? But that's another technicality that when you read papers or when you read I don't know, whatever's in the media, right? They'll say, oh, it's very it can store so much energy in such a little space. Okay, well, what is that space? What is that volume that you refer to? Is it normalized by the entire battery, like the volume of the battery itself? Or is it the volume of like the active material? So just lithium cobalt oxide versus sulfur, each of them have a different density and that's different volume when you have 1 mole of the material. So one has to be specific about that. And then the flow of the water. So if you're pouring your, the content of your Nalgene bottle out, that's the power. So how quickly, can you deliver the stored energy? That's what we're talking about when we talk about power. Does it flow very slowly? Does it flow very quickly? Right? That's the power. And so in terms of units and getting used to the units that we talk about, when we talk about energy, we talk about watt hours. And when we talk about power, we use the unit watts. So the example is if you have a 15 watt power LED bulb, that means it's going to instantaneously, the moment you turn it on, right? It's going to need 15 watts of power to power instantaneously. But then for it to run and be operational for an hour, that's 15 watt hours. That's the amount of energy that it uses, right? So there's a W in there, there's a WH in there, but those are the 2 technical definitions of power, energy, and the units associated with these metrics. I have a long list of terms because I would like for us to be on the same page, right? Because what is an anode? It's really just a negative electrode, but what makes something a negative electrode, right? So I want to be very clear about that. So I have like 4 or 5 slides on just technical definitions. Okay. So when I say active material, here's a battery. You see some active material here. So that's a lithium cobalt oxide. Green is the lithium. The blue is the cobalt oxide. And then the gray on the anode side are the sheets of carbon in graphite. And and the green again is lithium ions, right? So the active material, when we talk about that, it depends on if we're talking about the cathode or anode. If I'm talking about the cathode or the positive electrode, and I want to talk about, the active material, what is actually participating in reduction and oxidation and converting the chemical reaction into electrical energy, then I'm talking about the active material. I'm less interested in all the binder materials, things like that. That's not the active material. The active material is the material of interest that participates in the electrochemical reaction itself. The anode is the negative electrode in the electrochemical cell. The battery itself, that definition is one or more electrochemical cells. So when I talk about, here in this diagram, that is one electrochemical cell because I can identify the cathode, I can identify the anode, and then there's a separator, like a plastic physical separator that also is drenched in liquid electrolyte in this particular diagram. But in the electrolyte section, we'll also talk about solid electrolytes. Then capacity. There's a lot of talk about, how much capacity does a battery have, right? So the capacity is the quantity of electrical energy that can be stored and then delivered by the electrical chemical cell or battery. The caveat is the initial capacity is not always going to be the same as the capacity of the 10th cycle, when you discharge and charge a cell for the 10th time, the 100th time, right? We've all experienced this in our portable devices. When you have a battery, you notice that the time in between that you have to plug in your device decreases the longer you have your device. That means your battery capacity is decreasing over time. So that number is actually dynamic. It's not a constant number. It's dependent on the cycle, how many times you cycled your battery. The cathode is just the positive electrode in the electrochemical cell. So it's all relative, right? A cathode in one cell can be the anode in another cell. The cathode is positive because it's positive relative to that of the anode. So it's always positive. So just because I said lithium is the anode in the lithium cobalt oxide and a lithium ion cell doesn't mean lithium is always the anode. It could be a cathode. You just have to find a more negative electrode, right? So it's all relative. In our context, lithium will most often, if not always, be the anode, the negative electrode. And the cell is what converts the chemical energy into electrical energy. Charging. This is a term I've thrown out there. What exactly is charging? For lithium ion batteries, what I'm talking about is delithiation from the cathode. So here you see under charge, the lithium ions are moving from cathode over to anode. Okay. Some of the geometries that you've seen or will hear about are coin cells. So they look like button cells. They're referred to as button cells. When we also charge, we're charging at a constant current, right? We apply some constant current over the entire charging cycle. You can have variable applied current. There's no reason why you cannot, but more often than not, when people talk about the amount of current they apply to charge a battery, that is, it's under a constant value. And that's to delithiate a lithium ion battery, right? That's to remove lithium ions, move it from the cathode over to the anode. Some of the cells that you've seen are cylindrical cells, right? They have a cylindrical form factor. And the numbers that you may or may not have heard are 18650, so that's 18 millimeters in diameter, 65 millimeters long, right? So all these numbers have a rhyme and a reason, and so it's not the only dimension, but it's a popular dimension. All right, I want to be mindful of time, so we might have to, well, we would definitely have to pick up here next time. So I just want to wrap up with C rate and discharging. So C rate is the rate at which the battery is discharged relative to a maximum capacity, right? So when we say, oh, can a battery discharge very quickly, right? Can you get the power very quickly? There is a number called the C rate, but that's normalized. It's normalized to how much energy we can get out from the system. So different C rate. So you can have a different C rate for different materials or different batteries. So, just because something can operate under a high C rate, we have to see what it's actually normalized by. And then the last term on the slide, discharging. That's in the case of lithium ion batteries, that means you're lithiating, right? So during discharging, you're moving the green lithium ions here. Green in the schematic, lithium ions are not actually green. You're moving the lithium ions from the anode over to the cathode. So you're taking it from where it is, graphite, and moving it over to the lithium cobalt oxide crystal structure. All right, so we only have about a minute and a half left. So I want to make sure that there's a little bit of time for any questions so far. All right, the silence seems to indicate that there are no questions. One moment. Is 1C defined empirically or by calculation? Excuse me. I think by calculation, you mean like, is there a number that is accepted like a priori, like, right, as versus empirical, as in like you measure it and then you normalize the 1C? That's probably what you mean, correct?
Yeah, I was wondering, like, is it a matter of like trying to set a record, so to speak, with this particular system and then like basing things off of that, or is it just calculated?
So I suppose the answer is it's closer to calculation. Okay, I should clarify what I mean by that, because it's sort of a loaded answer. What I mean is operationally, you can define 1C however you want, but what people define 1C as is if you can discharge, right, an amp hour in an hour. So if, let's say, lithium cobalt oxide, you can get out like theoretical capacity, let's go off of that, is 272 milliamp hour per gram. So then you say, okay, can I get that out in 1 hour? 272 milliamp hour, that's one cell. Can I get that? I'm going to say that's 1C. That means I can get all of that out in 1 hour. That is extremely fast. But that is your definition of 1C. And you can, okay, well, we haven't gone into how you calculate the theoretical capacity of a material, but that's in lecture 3. But when we get there, you'll know. But right, so you say, okay, I can get 1C, which is I can get that amount of energy out in 1 hour. So that means what happens if I try to do that in half an hour? I try to push the system so I get all of this mass transport out, right, in half an hour. So that's C over 2, right? That's divided by 1C. That's C over 2. That's in 30 minutes. Can I do it in 30 minutes versus 1 hour? You can, but what happens is because you're trying to move, the short answer is because you're trying to move mass transport, and unlike photovoltaics that you've been learning where you're trying to move electrons and you think about electron mobility, you're now having to push a lithium ion through a material, like physically push through by applying current. And so doing anything fast is actually really difficult. So you can get less material out, less energy out, and move the ion. You can move it, but some of the ions will be stuck. There are a number of like just physical issues with moving ions that fast. So you get less capacity. So what the short of it is, 1C is defined by calculation, but 1C can change depending on what you as an experimentalist define it as. So if I said, well, I'm defining it by theoretical capacity, what you'll learn later on is lithium cobalt oxide, nobody removes an entire molar equivalent of lithium ions out because of structural collapse. So you engineer a system where you only remove, let's say 60% of the lithium ions. Then you can say, okay, well, if I only move 60% of the lithium ions, I only get 60% of my theoretical capacity. So I will define that as 1C. So 60% of 272, how, that is going to be 1C. How much of that I moved is in 1 hour is going to be 1C. So 60% of 272 is 163. So I can say, well, 1C for me, if I'm only moving 60%, is once I get up to 163 milliamp hours per gram in 1 hour, that is 1C. So it's very relative. I have many more examples, but we're also 2 minutes over. So I want to be very mindful of class time. But hopefully that answers your question. It sounds empirical, but it's not. It's based on the calculations of the material itself. Okay, if there are any follow-up questions, feel free to put it on the group discussion board so that everyone else can see your question and I can respond, and then we can all discuss together as a group. With that, I will see everybody on Zoom for Friday, 12:40. All right, thanks everyone.